we're going to talk about Taylor series and Taylor polynomials. Basically, when the Taylor remainder goes to 0, a Taylor polynomial can be extended into a Taylor series. Now, think about this. If we want to find a value like sine x, and x is not a special angle, say x equals 0.5, how do we actually calculate that? Sure, you can just punch it into a calculator and get the answer instantly. But how does the calculator know what to do? It actually uses the exact Taylor series we are about to discuss. In other words, calculators have a built-in program that is designed using the Taylor series for the sine function. This just shows you how incredibly important the Taylor series is when it comes to real-world applications. On this slide, we have a very important theorem, Taylor's theorem. When we differentiate a continuous function f, we get the function f prime of derivatives. But this new function f prime is not necessarily continuous. If f prime turns out to be continuous, we call the original function f continuously differentiable. If we are looking at a specific point c, we say that f has a continuous derivative at c, which just means the function f prime of derivatives is continuous at that point. Now, let's consider an open interval I. When we say that f has n plus 1 continuous derivatives on I, it means that at any point in this interval, we can differentiate f for n plus 1 times. In other words, the n plus 1 th derivative at exists, and that the n plus 1 th function f caret, n plus 1, of derivatives is also continuous at a. When this holds true, we can write f as the equation shown on the screen. This formula is what we call the Taylor expansion of f at point A. Finally, the expression in the very last line is crucial, and it is known as the Taylor remainder. Following up on Taylor's theorem, we can write the function f as a Taylor polynomial plus the Taylor remainder. The polynomial part is what you see in the second line. The full, formal name for it is the nth degree Taylor polynomial in powers of x minus a. Earlier, we saw that the remainder term r sub n plus 1 was written as an integral. Now, this slide shows us that we can actually write the remainder without using an integral at all, just like you see in the second to last line. The number c in this formula is some value between x and a, but we cannot pinpoint its exact value. Let's look closely at the roles of a and x here. Taylor's theorem tells us that we can create a Taylor expansion around a point A. This means it has to be picked ahead of time. Say, we choose to expand the function at a equals 1. But remember, this whole expansion is still a function of x. Since x is a variable, we can plug in any number we want, which means x could be larger than a or smaller than a. And that is exactly why the number c in the Taylor remainder is described as a number that lies somewhere between x and a. Let's assume j is the closed interval joining x and a, and remember that x could be larger than a or smaller than a. The very last line on the screen shows us how to estimate the upper bound for the remainder term r sub n plus 1. The first equation up there just puts absolute value bars around the Taylor remainder. Moving to the right side of the inequality, that first expression calculates the maximum absolute value of the n plus 1 th derivative across the whole interval j. This inequality makes perfect sense because the n plus 1 th derivative at that specific point c will definitely be less than its maximum value across the entire interval j. If we assume that the function f is infinitely differentiable, it just means that we can keep differentiating f forever, infinitely many times. Good examples of this are the exponential function e to the x and the sine function. When this happens, the Taylor expansion you see on the screen works for any positive integer n you choose. What we are looking for is that as n goes to infinity, the Taylor remainder goes to 0. When that happens, we can write the function f as a Taylor series, which is the expression right there on the screen. This Taylor series is expanded around point A because the whole thing is written in powers of x minus a. Now, when it equals 0, we give it a special name, the Maclaurin series. This is named after the Scottish mathematician Colin Maclaurin. First up, we want to derive the Taylor series for the exponential function e to the x. To make that happen, we have to prove that its Taylor remainder goes to 0. So, we will need to calculate a limit first to help us out, just like in the example below. In this example, we are calculating the limit shown in the second line. The variable x is just any real number given to us, and we are letting n go to infinity. Because x is picked ahead of time, we can definitely find a positive integer k that is large enough so that the absolute value of x is smaller than k. Now, let's also assume that n is larger than k plus 1. This gives us the equation in the second to last line. Look at the first expression on the right side of the equal sign. We have rewritten n factorial in the denominator using k factorial, and we have also rewritten k to the nth power in the numerator to include k to the kth power. You can see that the expression inside the middle square brackets is just a bunch of fractions multiplied together. Since every single fraction is less than 1, multiplying them all together is still less than 1. In the end, this leaves us with something smaller than the expression on the far right. Since the positive integer k is larger than the absolute value of x, the equation on the second line makes perfect sense, especially if you apply the formula from the second to last line of the last slide. Now, because k is a fixed number, as n goes to infinity, that expression on the far right of the second line is going to drop to 0. By the pinching theorem, the middle term has to go to 0 as well. You can see that right here in the very last line. In the end, this proves that even without the absolute value bars, the limit still goes to 0. Next, we're going to derive the Taylor series for the exponential function e to the x. So, let's look at the function f of x equals e to the x. We already know that no matter how many times you differentiate it, its nth derivative is always just e to the x. Now, if we expand this around to equals 0, we can use the previous formula for the nth degree Taylor polynomial to get the equation right here in the very last line. In order to extend the Taylor polynomial into a Taylor series, we need to show that the Taylor remainder goes to 0 as n goes to infinity. First, let's fix the value of the variable x, and let j be the closed interval joining 0 and x. Now, let's assume m is larger than the maximum value of the exponential function e to the x across this interval j. We can choose the value of m like this. If x is greater than 0, then m is taken to be e to the x. If x is less than 0, then m is taken to be e to the 0. Since any higher order derivative of the exponential function e to the x stays exactly the same, the inequality in the second line makes perfect sense. This m is the exact same one we just talked about on the last slide. If we apply the formula 1 from page 5 that we saw earlier, we get the upper bound estimate for the Taylor remainder, which is shown right here on the very last line. According to the example we did earlier, the limit of that second equation goes to 0. So, if we combine that with the very last line from the previous slide, we have successfully proven that as n goes to infinity, the Taylor remainder goes to 0. Now that the Taylor remainder goes to 0, we finally get the Taylor series for the exponential function e to the x shown right here on the screen. And since we are expanding it around to equals 0, this is also known as the Maclaurin series for the exponential function e to the x. In this example, we are going to derive the Taylor series for the sine function at a equals 0. This slide lists out the Taylor polynomials all the way up to the 8th degree. Since the derivatives of the sine function repeat in a cycle of 4, it should be pretty easy to come up with these 8 Taylor polynomials on the screen. To get the full series, we obviously need to show that the Taylor remainder goes to 0. Now, because differentiating the sine function over and over just gives us a cycle of positive and negative sines and cosines, the absolute value of these higher-order derivatives will always be either the absolute value of sine or cosine. This tells us that the absolute value of any derivative of sine is always less than or equal to 1, which can be seen in the very first equation on the second line. So, we can just set the m value to 1. If we plug this into the formula 1 from page 5 that we saw earlier, we get the upper bound estimate for the Taylor remainder, which is written right here on the third line. And from the example we did before, we know the limit of that expression on the right side of the inequality goes to 0. In the end, by using the pinching theorem, we have proven that the Taylor remainder goes to 0. Now that the Taylor remainder goes to 0, we finally get the Taylor series for the sine function shown right here on the screen. And since we are expanding it around it equals 0, this is also the Maclaurin series for sine function. In this example, we are going to derive the Taylor series for the cosine function, which, of course, is also a Maclaurin series. You can see the actual form of the series shown right here on the screen. In this example, we want to approximate the value of e with an error of less than 0.001. Because the Taylor remainder works as the error estimate, we are looking to make the Taylor remainder of e to the x smaller than 0.001 at x equals 1. Just like you see in the third line, we need to find an n value that makes 3 over n plus 1 factorial less than 0.001. The fifth line shows us that we can hit this target simply by setting n to 6. So, all we have to do is calculate the 6th degree Taylor polynomial of e to the x at x equals 1. And that final approximation is listed right here in the last line. In this example, we want to approximate the value of sine 0.5 with an error of less than 0.001. Because the Taylor remainder works as the error estimate, we are looking to make the Taylor remainder of the sine function smaller than 0.001 at x equals 0.5. Just like you see in the third line, we need to find an n value that makes the expression on the right side of that inequality less than 0.001. The fifth line shows us that we can hit this target simply by setting n to 4. So, all we have to do is calculate the 4th degree Taylor polynomial of the sine function at x equals 0.5. Since the 3rd degree and 4th degree Taylor polynomials for the sine function happen to be exactly the same, that final approximation is listed right here in the last line.